watch TV.
In 2005, U.S. Congress mandated the transition from analog to digital broadcasting, which began in 2009. The evolution towards digital television broadcasting came with a number of benefits: better quality picture, better sound, increased broadcasting security, and more over-the-air channels.
Hey, why don't we build a digital TV system for our capstone project?
Yeah, that sounds great. Let's start planning.
Digital TV in the US is based on the standard from Advanced Television Systems Committee, or ATSC for short. If we want to build our digital TV system, we have to understand the standard first. Once we know the system requirements, we can decide what platform to use. Digital TV is transmitted using ABS-V? What about OFDM?
Hey Hector, let's use the Z-board and the analog devices at Earthstar to implement our system. We will have two computers. One computer will be our transmitter and the other computer will be our receiver. And each computer will be attached to a Z-board. And also we can use software-defined radio to implement our system. What tools do you think we should use?
MathWorks has support for the Z-board and the analog devices board.
Here's how the system works. First, we started the transmitter with the video file represented by this football. Then the video file goes through the encoder to introduce extra bits and help correct errors later in the process. That is why the football just turned into a basketball. After that, field sinks, represented by the tape, are added to help the receiver identify the data frames to show where data starts. Finally, the data is modulated so it's ready to transmit over the air. The receiver gets the signal over the air and undoes everything done by the transmitter. The receiver demodulates the data, it removes the field sinks, decodes the data, and gets the original video file back.
Sounds like a good plan. Let's do it.
But wait!
An important aspect of the system is ensuring that the transmitter and receiver use the same carrier frequencies. Here, the carrier frequencies at the transmitter and receiver are represented by the two runners. They first start at different speeds, which represents both operating at different frequencies. The slower runner speeds up and matches the speed of the other runner, which represents frequency recovery. In order to correct the phase, or the distance between the two runners, the slower runner catches up to the other runner. The phase is now recovered.
Now that we have each of the blocks working, let's test out the system. We transmitted 10,779,392 pieces of data and spaced the transmitter and receiver further and further apart. Even up to 4 feet apart, we observed only 120,572 errors, thanks to the encoding and error correction used before transmitting. This corresponds to a symbol error rate of only 1.12%.
Let's see what the errors look like when the video is decoded. Here's a comparison of the transmitter and received videos.
He had one kick return for 58 yards in his one regular season game against his former team, the Vikings, and they just pop it up. Good kick.
As we can see, there is some distortion in the received image, which is caused by the errors that could not be corrected. Overall, the video still looks very clear.